Color charge is a property of quarks and gluons that is related to the particles' strong interactions in the theory of quantum chromodynamics. Note that the color charge of quarks and gluons is completely unrelated to visual perception of color. The term color became popular simply because the charge responsible for the strong force between particles can be analogized to the three primary colors of human vision: red, green, and blue. Another color scheme is red, yellow, and blue, using paint rather than light as the perceptible analogy. Particles have corresponding antiparticles. A particle with red, green, or blue charge has a corresponding antiparticle in which the color charge must be the anticolor of red, green, and blue, respectively, for the color charge to be conserved in particle-antiparticle creation and annihilation. Particle physicists call these anti-red, anti-green, and anti-blue. All three colors mixed together, or any one of these colors and its complement, is colorless, or white, and has a net color charge of zero. Free particles have a color charge of zero. Baryons are composed of three quarks, but the individual quarks can have red, green, or blue charges, or negatives. Mesons are made from a quark and antiquark. The quark can be any color, and the antiquark will have the negative of that color. This color charge differs from electromagnetic charges since electromagnetic charges have only one kind of value. Positive and negative electrical charges are the same kind of charge as they only differ by the sign. Shortly after the existence of quarks was first proposed in 1964, Oscar W. Greenberg introduced the notion of color charge to explain how quarks could coexist inside some hadrons in otherwise identical quantum states without violating the Pauli exclusion principle. The theory of quantum chromodynamics has been under development since the 1970s and constitutes an important component of the Standard Model of particle physics. Red, green, and blue. In QCD, a quark's color can take one of three values or charges: red, green, and blue. An antiquark can take one of three anticolors, called anti-red, anti-green, and anti-blue. Gluons are mixtures of two colors, such as red and anti-green, which constitutes their color charge. QCD considers 8 gluons of the possible 9 color-anticolor combinations to be unique. See 8 gluon colors for an explanation. The following illustrates the coupling constants for color-charged particles. The quark colors combine to be colorless. The quark anticolors also combine to be colorless. A hadron with 3 quarks before a color change. Blue quark emits a blue anti-green gluon. Green quark has absorbed the blue anti-green gluon and is now blue. Color remains conserved. An animation of the interaction inside a neutron. The gluons are represented as circles with the color charge in the center and the anti-color charge on the outside. Field lines from color charges analogous to an electric field and electric charges. The strong force acting between color charges can be depicted using field lines. However, the color field lines do not arc outwards from one charge to another as much, because they are pulled together tightly by gluons. This effect confines quarks within hadrons. Coupling constant and charge. In a quantum field theory, a coupling constant and a charge are different but related notions. The coupling constant sets the magnitude of the force of interaction. For example, in quantum electrodynamics, the fine structure constant is a coupling constant. The charge in a gauge theory has to do with the way a particle transforms under the gauge symmetry, i.e., its representation under the gauge group. For example, the electron has charge -1 and the positron has charge +1, implying that the gauge transformation has opposite effects on them in some sense. Specifically, if a local gauge transformation is applied in electrodynamics, then one finds and where is the photon field, and psi is the electron field with Q equals -1. Since QCD is a non-abelian theory, the representations, and hence the color charges, are more complicated. They are dealt with in the next section. Quark and gluon fields and color charges. In QCD, the gauge group is the non-abelian group SU. The running coupling is usually denoted by alpha S. Each flavor of quark belongs to the fundamental representation and contains a triplet of fields together denoted by psi. The antiquark field belongs to the complex conjugate representation and also contains a triplet of fields. We can write and the gluon contains an octet of fields, and belongs to the adjoint representation, and can be written using the Gell-Mann matrices as. All other particles belong to the trivial representation of color SU. The color charge of each of these fields is fully specified by the representations. Quarks have a color charge of red, green or blue, and antiquarks have a color charge of anti-red, anti-green or anti-blue. Gluons have a combination of two color charges in a superposition of states which are given by the Gell-Mann matrices. All other particles have zero color charge. Mathematically speaking, the color charge of a particle is the value of a certain quadratic Casimir operator in the representation of the particle. In the simple language introduced previously, the three indices 1, 2, and 3 in the quark triplet above are usually identified with the three colors. The colorful language misses the following point. A gauge transformation in color SU can be written as psi U psi, where U is a 3×3 matrix which belongs to the group SU. Thus, after gauge transformation, the new colors are linear combinations of the old colors. In short, the simplified language introduced before is not gauge invariant. Color charge is conserved, but the bookkeeping involved in this is more complicated than just adding up the charges, as is done in quantum electrodynamics. One simple way of doing this is to look at the interaction vertex in QCD and replace it by a color line representation. The meaning is the following. Let psi represent the ith component of a quark field. The color of a gluon is similarly given by A, which corresponds to the particular Gell-Mann matrix it is associated with. This matrix has indices I and J. These are the color labels on the gluon. At the interaction vertex 1 has chi Gj plus Qj. The color line representation tracks these indices. Color charge conservation means that the ends of these color lines must be either in the initial or final state, equivalently, that no lines break in the middle of a diagram. Since gluons carry color charge, two gluons can also interact. A typical interaction vertex for gluons involves G plus Gg. This is shown here, along with its color line representation. The color line diagrams can be restated in terms of conservation laws of color. However, as noted before, this is not a gauge-invariant language. Note that in a typical non-abelian gauge theory, the gauge boson carries the charge of the theory, and hence has interactions of this kind, for example, the W boson in the electroweak theory. In the electroweak theory, the W also carries electric charge, and hence interacts with a photon.